Welcome back to my channel. Today I am in front of you with my second lecture of physical world, in which we will discuss here about the fundamental forces in nature. So fundamental forces in nature means that we will discuss here about the basic forces in nature. These forces are four types here, which are in front of you. So first one is that gravitational forces, which is which you read in your class 9th. Second one is that weak nuclear forces. Third one is that electromagnetic forces. And fourth is last, which is strong nuclear forces. And I have written the all forces according to their increasing strength. Means that the weakest force is gravitational force, and second weakest is weak nuclear forces, and third one is that electromagnetic force, and fourth is strong nuclear forces. And before their brief discussion, I will write here the ratio, which is very important for you for MCQ question. What will be the ratio between these type of forces? So see here, student, the ratio between the gravitational force, weak nuclear force, electromagnetic force and strong nuclear force will be equal to 1 ratio 10 raised to the power 25 ratio 10 raised to the power 36 ratio 10 raised to the power 38. In some books, in place of this, it is in place of 25 and 38 written 26 and 39. So this one will be the ratio between their strength. So after this I will write here the explanation one by one. So first topic I will start in front of you, which is gravitational forces. So student, let's start the video. So here when we talk about the gravitational forces, it means that this force. So the statement about the universal law of gravitation. It means that every object in the universe attracted by each other, a type of force, with a type of attraction force, you can say, which is called gravitation force. So for this force, Newton gave a relationship which is called Newton's law of gravitation, or which is Newton's formula for gravitational force. Newton gave a relationship for this attraction force, and he explained that the force of attraction, because gravitational force is only on type of one force, which is called attraction force. It is only attraction force. So Newton said force of attraction or gravitational force between two bodies placed anywhere in the universe is directly proportional to product of their masses. Because you know that you have two bodies, or you can say two objects placed anywhere in the universe. Suppose two objects of mass m1 m2 placed anywhere in the universe at distance r, then the force of attraction, which is called gravitational force between them, is directly proportional to the product of their masses and inversely proportional to square of the distance between them. And after taking these two relations, I will write here F is proportional to m1 m2 by r square. And after removing this proportionality sign, I will use here a constant which is called proportionality constant G into m1 m2 by r square. This proportionality constant G is called universal proportionality constant. Clear, student? And the value of G is 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. This is the value of this capital G, which will be constant for the universe, and the value for whole universe is constant, which is equals to 6.67 into 10 raised to the power minus 11 Newton meter square per coulomb square. So after this formula, you can check what is the value of force between these two bodies if suppose their mass is 1 kg, both of the bodies are placed. So if suppose their mass is 1 kg and both of the bodies are placed at 1 meter. So for this, if I will write here, if suppose mass of two bodies is 1 kg and they both are placed at 1 meter, so we want to check the force of attraction, means gravitational force between them is F is equals to G m1 m2 by this formula r square. G remain as it is, m1 m2 over 1. So by solving this, we will get the value Fg is equal to capital G, because the all values equals to 1, and you know the value of capital G, which is equal to 6.67 into 10 raised to the power minus 11 in numeric form, and the unit for this is Newton, because here we are calculating the force. So you can say that if the two objects of 1 kg placed, or you can say separated at 1 meter distance, the force of attraction, which is called gravitational force of attraction between them, is 6.67 into 10 raised to the power minus 11, which is very small. Clear? So after this discussion, I will write here some important characteristic of gravitational forces. So before the important characteristic, I will explain one thing here. Suppose I am taking one example of two bodies. One is Earth, other is another object of mass m. So the formula of gravitation for them is equals to G MEM by R E square, means that this object plays on the surface of Earth, then I will use here the radius of Earth. And we will see that the force of attraction, which is called gravitational force, is applied by this Earth on that object is Fg, which is equal to the whole value, and the same force is applied by this object to the Earth. But we will see on this time the smaller object attracted toward the Earth, but Earth will not. Why? Because of size of Earth. The size of Earth is very huge, so it can't displace their position, but it experiences the equal force as the force experienced by the particle or by the object of mass smaller. So mind this point. After that, beta, I will write here the important characteristic of gravitational force. So see here. So student, see here, I have written some important points or important characteristic of the gravitation forces. So first one is that these forces are always attractive forces, means they are always attractive in nature. Second one is that they are central forces, means that from the center of one object they act between the center of one object to center of other. So that's why we can say they are central forces. After that, they are conservative in nature. In nature they are conservative, means these forces are conservative in nature. After that, long range forces, because you know that in universe between two bodies is placed at anywhere in universe feel this force, which is called gravitational force. So it is a long range force. After that, they obey inverse square law, because the force is inversely proportional to square of the distance. Then last one is that second last, you know that initially I told you this force is the weakest in nature. So it is our weakest force. And last point is that, which is very important for your MCQ, the field particle of gravitational forces is graviton. Every type of fundamental forces has field particle. So after that, student, I will explain the second one is that which is weak nuclear forces. Here, when we talk about the second weakest force, which is called weak nuclear forces, so in this case, you know that it is already written here nuclear forces. It means that this force will come into play in case of nuclear reaction. So the main advantage, you can say, how this force were discovered. So see here, this force, weak nuclear force, were discovered during the study of beta decay in radioactive elements or in radioactive nucleus. During the beta decay, you can see that this force will come into play, or you can say that the weak nuclear forces were discovered during the beta decay of a radioactive nucleus. So here, when the beta decay will occur in the nucleus, that time the beta particles which contain high energetic electrons or positron emitted from the nucleus. It was supposed that, or you can say that, assume that when the beta decay occurs in neutron, then neutron is divided in two parts. One is proton and other is electron. So when this two part is when the neutron is divided by two part, proton and electron, and after that the Pauli in 1930 gave a postulate that in which an uncharged elementary particle known as antineutrino also emitted along with this beta particle from the nucleus, or from the neutron, or you can say that during the beta decay of neutron. So here, during the beta decay of neutron, three type of, you can say that during the beta decay of neutron, the neutron is divided in three parts: proton, electron, and after that, by the Pauli hypothesis, in antineutrino. This is our antineutrino, which has zero charge and rest mass. So when the beta particle, he said, when the beta particle along with Pauli said, along with the emission of beta particle from the nucleus during the beta decay, an uncharged particle which is called uncharged and rest mass particle which is called antineutrino is also emitted. And we know that in this beta particle, high energetic electrons, and, or you can say electrons, high energetic electrons or positron are emitted from the nucleus. So when this high energy electron emitted from the nucleus, their energy varies from the value of 0 to maximum value. Clear, student? Their energy varies from 0 to maximum value. And for all beta particle, means that for during the beta decay of nucleus, for all beta particle, means for all emitted beta particles, they have same energy and same velocity. So Pauli said that when this antineutrino particle, which is rest mass or no charge and rest mass particle, emitted along with this beta particle, so they both have energy and they share their energy between them. Means beta particle, or you can say that electron, which is high energetic inside the beta particle, and the antineutrino share their energy between them. So when the energy of electron is higher, that time the energy of means that when the energy of electron is maximum, that time the energy of antineutrino is minimum. And on the other hand, when the energy of antineutrino is maximum, that time the energy of electron is minimum. Clear, student? So during this type of formation, a type of force act between them, and this force is called weak nuclear forces. Hence we can say that the weak nuclear forces from here act between electrons and antineutrino. They both are they both are short lifetime elementary particle. Short lifetime elementary particle. Say that the weak nuclear forces act between those particles or those elementary particles which have short lifetime. So here the definition of weak nuclear forces, at last you can say that the weak nuclear forces are those forces which act between those elementary particles which have short lifetime, like electron and antineutrino. Or the second one is that you can say that lepton star and lepton, clear, and lepton, one pair is and meson. Clear, student? So this one is, these are the, you can say that these are the elementary particles, light elementary particles having short lifetime, which feel the force of, which feel the weak nuclear force between them. So in short you can say that the weak nuclear forces comes into play during the beta decay of the nucleus, in which when the beta decay occurs in neutron, the neutron is divided in two parts, proton and electron, and after Pauli postulates, Pauli said that a uncharged particle, elementary particle, is also emitted with the beta particle during the beta decay of neutron, which moves with same energy and same velocity with as beta particle, and they share their energy between them. Means that the beta particle energy, beta, as you know that the beta particle consists here and high energetic electrons. So the high energetic electrons and the antineutrino share their energy. When the high energy means when the electron energy is high, that time the antineutrino has minimum or low, or vice versa. Hence, at last, we can say that the conclusion is that the force of attraction between these two is called weak nuclear force. And on the other basis, because these two have short lifetime, we can say that the weak nuclear forces act between those light elementary particles which have short lifetime. So this one is the study of weak nuclear force, which is complicated for you. So I will write here in short way. I will write here short points to understand the weak nuclear force. So see here. So here, student, I have written the statement to save our time and data here about the weak nuclear forces as I discussed here. So see, once again I repeat it. So weak nuclear forces comes into play during the study of beta decay of nucleus. Clear? So because you know that it is impossible to get any kind of energy from the nucleus by normal reaction, that's why this type of linear reaction, or you can say this type of force, is important for nuclear reaction. So here, after, see here, the beta decay of neutron is divided in two parts. One is proton, other is electron. And in case of beta decay, the high energetic electron or positrons, which are called beta particles, are emitted through the nucleus. When the beta particle is emitted through the nucleus, after some time Pauli postulated that along with this beta particle, an uncharged particle which is called uncharged light elementary particle, which is called antineutrino, also emitted from the nucleus. And when the high energetic electrons, or you can say electrons, which are beta particles emitted from the nucleus, they have high energy and which vary from 0 to maximum value. Energy of this beta particle, because earlier it was proposed that, or it was given that a light elementary particle is emitted with this beta particle is shared between them, means the energy, high energy, is shared between the electrons and the antineutrino. When the energy of electron is maximum, that time the energy of antineutrino minimum, and vice versa. So because these two particles have short lifetime, so we can say that similarly the other light particles, those have short lifetime. Between them they interact with each other by a force which is called weak nuclear forces. So at last I have written the final definition. Means that the weak nuclear forces comes into play, or you can say that the weak nuclear forces which act between the two light elementary particles which have low lifetime or short lifetime. And the example for that I have written there. Examples for that is lepton lepton, lepton star lepton, between them lepton and lepton star, and second is lepton and meson. Student, these are fundamental light elementary fundamental particles. Clear, student? So you here in your physics you will discuss about three type of fundamental particles, but these are light elementary fundamental particles. You will discuss these fundamental particles in your higher classes, BSc and SC. Okay. So after that, student, I am writing some important characteristic about weak nuclear forces. First is that these forces are second shortest forces. One is that. Second is that it is, or you can say that these are 10 raised to the power 26 times stronger than gravitational forces. After that, third one is that these forces act between, as I discussed earlier, act between light elementary particles of short lifetime, known as lepton star lepton and lepton to meson. Clear, student? So these are the properties of weak nuclear forces, and after that I will start here the new topic which is called in case of electromagnetic forces. Here we will discuss about the forces which act between electric field and magnetic field. Normally when we discuss here about the electromagnetic forces, so specially we will discuss about the forces which act between the two charged particles. So when the force act between the two charged particles, this type of force is called electrostatic force. When the charged particles are at rest, and the force of interaction between the two charged particles is given by Coulomb, which is called Coulomb's law of electrostatic forces. So see here, I will write here these forces act between two charged particles. Forces act between two charged particles. So if suppose I have two charged particles of charge q1 and q2 placed at distance r. Suppose this one is our charge q1 and this one is charge q2, so placed at distance r, and these are the center because these forces are also central forces, so the force act between from the center of one charge to the center of other charge. So Coulomb said that the force of interaction between these two charge particles is directly proportional to the product of their charges, and the force which act between two charge particles is inversely proportional to the square of the distance between them. So after that, you will see when you will combine these two equations, you will get q1 q2 by r square, and after removing this proportionality sign, I will write here a constant which is called proportionality constant k, q1 q2 by r square. And here in electrostatics, because when we talk about the charge particles, means we are talking here about the electrostatics, so I will substitute here the value of k, which is equals to 4 pi epsilon naught, 1 over 4 pi epsilon naught. So I will substitute this value here. So at last I will see the value of force which is called electrostatic force, or you can say the electrostatic force between these two charge particles is this. So student, here what is the value of k? Here k is called proportionality constant, and the value, or you can say that electrostatic proportionality constant also. So the value of k is 1 over 4 pi epsilon naught. Here the epsilon, meaning of epsilon naught, if you will see here, the meaning of epsilon naught is electric permittivity in free space. Electric permittivity in free space. Clear student? And if you want more about the value of k and value of epsilon naught, then you can see here the value of k, which is equals to 1 over 4 pi epsilon naught, is equals to 9 into 10 raised to the power 9. If you want to write their unit, so you can say that Newton meter square per Coulomb square, because the SI unit of charge q1 q2 is Coulomb. You read this unit in your class 10th class. Clear student? So I will write here this way, or you can write the value of epsilon naught. If you want to write the value of epsilon naught, which is equals to 8.85 into 10 raised to the power minus 12, and after that if you want to write their SI unit, so you can say that Coulomb square per Newton meter square. If you are thinking that how I am writing this value and this value, so you can see here, when we talk about SI unit of k, you can interchange these two, Newton into meter square upon Coulomb square. And if you want to write the SI unit of this epsilon naught, you can interchange this and this. This will come here and this will goes up. So then you will get Coulomb squares over Newton meter square. Clear student? So this is your the value of epsilon naught. So this value is called, when we read this symbol, so we will use the word epsilon naught. Epsilon naught. Naught means for vacuum. Epsilon. Clear student? So these this is the explanation of electromagnetic force, in which we discuss here about only the force which act between two charge particles q1 and q2 placed at distance r. So after that, here I will write some important characteristic about the electromagnetic forces, which are much similar than gravitational forces. Important characteristic of electromagnetic force in the sense of two charges. As I discussed before this, the force of interaction act between two charges is attractive or repulsive, it depends on the nature of charges. If suppose the two charges of if suppose the two charges are same kind, then the force of interaction between them is repulsion. And if suppose the two charges of different kind, if suppose the two charges are different kind, means one is positive, other is negative, then the force of interaction between them is attractive. So here I have written some points regarding the electromagnetic forces, which are called important points. So see, first one is that the forces are attractive and repulsive in nature. The forces are attractive and repulsive in nature. It means it depends on nature of charge. If both charges are same kind, then force is repulsive, and different kind, the force will be attractive. After that, these are central forces, means it acts between the center of one charge to center of other charge. Clear? And these forces are conservative in nature as the gravitational forces. So conservative in nature. Clear, student? After that, they obey inverse square law, means that the force of interaction act between these two charged particles is inversely proportional to square of the distance between them. And next time, this force, which is called electromagnetic force or electromagnetic forces, are 10 raised to the power 36 times stronger than the gravitational forces. And then they act between two charges at a sufficient distance. When they placed at sufficient distance, then the force act between them is called electromagnetic forces. They are not applicable for very long distances. Clear, student? So this is applicable not much larger distance. Clear? So this act between not much larger distance means that it is applicable on sufficient distance, 1 meter, 50 centimeter and all. After that, the field particle for these electromagnetic forces is photon. In the previous cases, I discussed here about the field particle. At last, I will write all the field particles in different type of fundamental forces. So after this, student, I will start my last topic of fundamental forces, which is called strong nuclear forces. So let's see. So see here, our fourth topic is strong nuclear forces. In these forces, we will talk about the force which act between two proton and neutron in the nucleus. As you know that in the nucleus, proton and neutron bind together, and they bind together because of this strong nuclear forces. Means that strong nuclear forces are the forces which bind neutron and proton in the nucleus together. Clear, student? So this force is applicable for two protons, means proton-proton. It acts between proton-proton and proton-neutron and neutron-neutron pair also. So when we talk here about the nucleus in which proton and neutrons are situated, so that time we can say that if the distance between proton and neutron is less than, means you can say that if the distance between proton and neutron is larger than 10 raised to the power minus 15, that time the force act between them, which is called strong nuclear force, is attractive in nature. Cause of this, they bind together. But when the distance between them is much closer than 10 raised to the power minus 15, that time when these two particles comes much closer than, so that their distance between them is less than 10 raised to the power minus 15, which is called 1 Fermi distance. So after this, when they comes more closer than 10 raised to the power minus 15 meter, this attractive force is converted into repulsive force. So this is applicable only up to the distance which is called 10 raised to the power minus 14 meter. So this force is applicable up to a limited range, and below this range when we go, then we see that the force of attraction, which is called strong nuclear force, is goes to repulsion force. Clear, student? So here I will write some properties about this strong nuclear forces, which are called important characteristic property of strong nuclear force. So student, you can see here the important characteristic of strong nuclear forces, which in front of you I have written. So first is that you know that these forces are strongest in nature, and second one is that these are non-conservative forces as the weak nuclear forces also. Next one is that they do not obey inverse square law. Weak nuclear forces also do not obey inverse square law. And after that, you can see these forces are applicable up to a short distance, which is up to 10 raised to the power minus 14 meter. If the two bodies, or you can say proton, and distance between proton and neutron is much closer than the Fermi distance, then this force, which is basically in attractive in nature, is converted into repulsive nature. So here next one is that these forces are basically attractive in nature up to this distance. After that, the characteristic of this force is diminished when the distance between them becomes 10 raised to the power minus 2. When the distance between them comes closer to the distance which is called Fermi distance. So these forces are 10 raised to the power 38 times stronger than the gravitational force. As I discussed, these are the strongest in nature. So these are the forces which are much stronger, or you can say that which are strongest force in nature. So when we talk about their field particle is pi meson. So the field particle which is missing, field particle is pi meson. So for this force, the field particle is pi meson, and this force is strongest in nature. So after that, I will write all type of fundamental forces and their field particle chart. So here student, I have written the name of fundamental forces and their respective field particles which carries these forces in the field, So first one is that gravitational force, the field particle is graviton. Second one is weak nuclear force, the field particle is W and Z boson, light element. These are light elementary particles, and the electromagnetic force is photon. And next one, strong nuclear force is pi meson. So these are the field particles of their respective fundamental forces. So this field particles, this topic is important for your MCQ type of questions. Thank you for watching this video, student.